Hello, fellow scientists. My name is Shawn Cole,
My name is Chandra Thapaliya.
and today we'll be presenting a topic of a combination of nanoscale modeling and experimentation of catalysis for energy production applications.
So what is catalysis? According to the Merriam-Webster, catalysis is the process that increases in the rate of chemical reaction induced by material unchanged chemically at the end of the reaction. The material which remains unchanged is a catalyst which is structure that reduces the activation energy barrier between the reactants and the products. Why is catalysis important? Catalysis is important in the field of designing and engineering that has been used for the identification, understanding, prediction, control, and the various processes. These processes have the potential to address key global energy concerns. And how can we do this? Is through the designing of fuel cell and engineering. The applications. According to the United States Department of Energy, the fundamental scientific principles enabling rational catalyst design and chemical transformation control, and the research includes construction of the catalytic sites at the atomic levels, metal clusters, the development of theory, modeling, simulation of catalytic pathways. The primary emphasis of the DOE is the conversion and the use of fossil and renewable energy resources and the creation of advanced chemicals.
So, two developmental approaches given by the DOE would include experimental and computational efforts. Experimental efforts include processes such as impregnation methods, which is basically a method or various methods used for loading metal precursors onto carbon substrates, typically. This is for the research application with metal clusters, for instance. And inversely, with the same topic of research, we see computational efforts using density functional theory methods and also transition state methods. With DFT methods, we're able to locate a stable electronic structure of a cluster, and then after that, we're able to take that cluster and study transition state theory in order to find a most favorable reaction pathway. Now, advantages of experimental include the higher precision, and also we're able to get images of particles as our output. Whereas the primary disadvantage is it's just expensive to pay for the precursors or any other material that's needed. With computational, we have advantages of it being less expensive in that we only have to buy software and also licenses to go along with the software. But the primary disadvantage is we're only able to see digital output. So it's nothing that's quote unquote real life as it would be with experimental.
The examples of technique exploration, there are two types of technique exploration. There are Fishcher-Tropsch synthesis and protein exchange membrane fuel cell. Fishcher-Tropsch synthesis is a chemical catalyzed reaction involving the production of liquid fuels from syngas, whereas the proton exchange membrane fuel cell promotes the efficient generation of clean renewable energy from liquid and gaseous fuels.
So Fischer-Tropsch synthesis was first studied in 1925 when it was discovered that we're able to cross a mixture of hydrogen gas and carbon monoxide gas over a metal catalyst. And in industry today, we see that cobalt, and iron catalysts are the most used, but the most active would be ruthenium. However, it's too expensive. So we're able to use coal, natural gas, and biomass as feedstocks, as seen in the diagram to the right. And we take cobalt and iron-based catalysts and alloy them with different metals or co-catalysts using catalyst design and engineering to increase the efficiency and also reduce the cost of the metal catalyst that's used. On the other hand, we have proton exchange membrane fuel cells, which have been seen over the past 10 years to show progress. Proton exchange membrane fuel cells are able to, as we previously mentioned, generate clean renewable energy. And this is by feeding a fuel directly into the fuel cell, as seen in the GIF to the right, which is a hydrogen fuel cell. We feed hydrogen at the anode catalyst, and at the anodic catalyst, an oxidation process occurs which releases protons and electrons. The protons then cross over a porous proton exchange membrane, and the electrons travel through an electrical circuit which generates the energy that we would like to garner. And then at the cathodic catalyst, a reduction process occurs, whereas the protons, electrons, and oxygen from air reunite and are released through the exhaust pipe. And just as with Fishcher-Tropsch synthesis, the efficiency, durability, and cost can be reduced using catalyst design and engineering with metal alloy with co-catalysts.
In conclusion, what is understood is experimental methods are become more expensive with time. Computational methods are cheap and even become cheaper as the computers become more powerful, and the potentiality of the engineering metal surfaces to yield better catalytic properties.
So with that being said, it's good to remember that with an ideal catalyst, it's pretty much like practicing a balanced diet. And with a bad catalyst, it's like having a diet of fast food. With ideal catalyst, we're able to, or a balanced diet, we're able to get lasting energy. We're able to be peppy and get have a lot of productivity throughout our days. It also provides satisfaction. It fills us up. But the main thing is it's healthy. On the other hand, with a bad catalyst or fast food, we become lazy and slow, and we want to sleep. We're not as productive. And although it fills us up, and it also keeps our wallets full because it's inexpensive, the thing that we need to remember is that it's unhealthy. So which one would you rather have? Thank you.